All right, so we'll just do nomenclature of carboxylic acids. We'll start out with carboxylic acids and kind of move through the series in a semi-logical order. All right, so just like with any sort of naming system, identify the longest carbon chain. Try to have your functional group at the lowest number. So we go 1, 2, 3, 4, 5, 6. So the parent for this molecule will be a hexane, right? Pretty easy to remember. However, we're not going to use the suffix ane because that's for alkanes. This isn't a true alkane anymore. However, we can use that prefix, which is hexane. And then to indicate that it's a carboxylic acid, we're going to go with oic acid. So really, it's not that bad. You just swap off the E for an oic acid, and you've got the corresponding acid name. There are a lot of other old school names that have tended to stick around. All right, and let's take a look at the first one. What would this be called according to the method shown above? Be called methanoic acid? If you said, I need a bottle of methanoic acid, people would look at you funny. They'd be like, what the heck are you talking about? This is formic acid. Again, it's just an old school name that stuck around. When I was a kid, I was weird, and I used to crush ants. I know they say if you like harm animals, it's a high likelihood that you're a serial killer, but I'm not. I was just a weird kid, and I remember I would crush ants, and then I would smell my hand, and it smelled weird. That's formic acid. I didn't know that until I opened a formic acid bottle, and I was like, that smells just like crushed ants. They actually use it as a defense mechanism. So some ants will spray formic acid to defend themselves. Yep.
Isn't there centipedes or millipedes that do that?
Yeah, there's a lot of insects will use formic acid. Cyanide, I'm not sure. I'd have to look into that.
I think so.
Yeah. Yeah, insects are weird. All right. So there's this next one. All right. If we followed the naming system above, this would be ethanoic acid. Again, people would look at you funny if you asked for a bottle of ethanoic acid. Instead, people will call this acetic acid. Does anybody know what acetic acid is even more commonly referred to as in the kitchen? Vinegar. Yeah, so it's the main component in vinegar. The vinegar you use at home is usually like 5% acetic acid and water. You wouldn't want a full bottle of pure acetic acid to go in a salad. That would be a bad time. All right. All right, and then next, again, most people wouldn't be offended if you were to call this propanoic acid. However, the old name kind of stuck. Propianoic acid. And I think, honestly, it just flows better saying it that way, so the name just kind of stuck. This stuff, holy cow, it smells like the worst BO imaginable. So we'll make a note. Yeah, it smells like, imagine a high school locker room where nobody took their clothes home. That's what this smells like. All right. BO, for those of you that don't know, stands for body odor. It's just a polite way of saying it. All right, and then the next one is often called butyric acid. This smells like rotting butter. Or like, have you ever smelled milk that's gone bad, or any dairy product like that's been left out unrefrigerated for a week? That's kind of what this smells like. So it smells like rotten dairy. Has anybody seen, I think it's on the Discovery Channel, that show where the whaling ships go out, and I think they're called the Sea Shepherd, and they harass the whaling boats in Japan? It's Whale Wars? Yeah. So in Japan, they still hunt whales down near the Antarctic, and so there's these advocacy groups that go out and harass them to try to save the whales. On the show, they actually get bottles of butyric acid and will huck them at the whaling ships, because once this gets into whale meat, nobody will want to eat it. It smells like rotten dairy. So they do it both to harass the whaling ships and to spoil any of the meat that they manage to have on board. So pretty nasty stuff. All right, that's the last of the super duper smelly ones. Yeah. Oftentimes low molecular weight organic molecules that are either aldehydes or carboxylic acids smell bad. I'm not sure why those two functional groups in particular do. The ones that smell good are esters. Why esters smell good and carboxylic acid smell bad, I'm sure there's some sort of evolutionary process going on there. Yeah.
I was about to say, it's like the confidence hypothesis is that it helps us our ancestors detect spoiled.
Yeah, I'm sure it had to do with detecting spoiled foods in some way, shape, or form, or just knowing where danger was, even from insects, right? Formic acid sprayed in your face, you're probably like, that's not a good insect. I should not eat that. All right, what's this one called? Benzoic acid. We've seen that. So that's another non-IUPAC one. And then there's one kind of oddball one. They just call this cyclohexane carboxylic acid. Kind of like they gave up, didn't know how to name it, and they're like, well, it's kind of both, so let's just call it cyclohexane carboxylic acid. All right, so those are kind of the somewhat common non-IUPAC named acids, but let's take a look at the ones that you'll see a lot in biochemistry. And these are called diacids. So what happens when you have more than one carboxylic acid? How many of you are going to take biochemistry? Oh, that's good. I like this. All right, so the simplest one is 2 carbons. So it's an ethane with a carboxylic acid coming off of each end. We can extend this out. So let's just draw the series first. This one has 3 carbons. Then we'll do 4 carbons. And then we'll go all the way to 5 carbons. And then we'll go to 6 carbons. Wait, no, am I doing this right? 1, 2, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 carbons next. And then one more. All right, so let's start with this one. You're going to wonder why I'm starting with this one, but it's something we've all made. What's this one called? What's that? Adipic acid. You remember when we did the ring opening of cyclohexane, we made adipic acid? Again, you can tell that this is not IUPAC named because it's got 6 carbons in there, but it doesn't have the hex prefix anywhere to be seen. So adipic acid's one we're familiar with. Now let's go back and fill in the other ones. The first one was called oxalic acid. Then there's malonic acid. Like I said, a lot of these will show up in biochemistry courses. And there's succinic acid. And then there's glutaric acid. And then, like we said, adipic acid was one we've seen previously. And then there's pimelic acid. PIM, sorry. Oop. Oh, that looks funny now. Let me fix that. No, it's okay. Oh, that still looks funny, but you get the idea. All right. These, I remember when I was reviewing biochemistry, I had a heck of a time remembering these. So I'll show you what we came up with while I was in grad school. Oh my, comma, such good apple pie. You're going to take biochemistry and be like, I'm glad Jeff told me this. You know why? O-M-S-G-A-P. So if you remember, oh my, such good apple pie, it'll help you remember the order of the diacids, which is kind of useful because they're not commonly used outside of biochemistry, but they are thrown out a fair amount in biochemistry courses. Make sense? All right. So let's briefly look at the structures and properties. All right, so let's think about a generic carboxylic acid. What makes it special? What do you think? Hydrogen bonding, so H bonds. Think about its pKa. Is it acidic? I would hope so, it's in the name. So the pKa of most is going to be around 5, which means it's relatively acidic. There are some that have pKa's closer to about 1. What do you think could drop it 4 orders of magnitude in terms of pKa units? Not quite. Not quite. So we're going to stick to regular acids. Induction, right? If this R group is a CF3 group, that's trifluoroacetic acid. That's actually a really strong acid compared to regular acetic acid. So sometimes you see trifluoroacetic acid used just to amp up the acidity. And then the last one is they tend to have kind of high boiling points. And let's take a look at why, and it's kind of related to the first 2 things above. Let's imagine we've got another molecule kind of hanging out. Like this, right? Molecules could float around in solution and find one another. Because that hydrogen is really acidic, it's going to hydrogen bond to another carbonyl. Same thing with that one. These carboxylic acids are notorious for dimerizing with one another. And when they dimerize, because you have 2 connection points, they really hang on for dear life. That tends to increase the boiling points and melting points of carboxylic acids. It requires more energy to rip these apart. Make sense? All right. So later on in the chapter, we'll go through and we'll talk about the nomenclature for acid halides, same thing with esters, same thing with anhydrides and nitriles. But for right now, we're going to focus on the carboxylic acids themselves. So now we get to talk about how we make carboxylic acids, but luckily we've seen a ton of this already. So we're just going to do some review. So I'm going to write down these reactions. I want you to fill in what goes into the spot with the arrow. So this will be good review. There's a lot of them. Some of these are quite old, some are way newer. So let's see with the show of fingers. How many of these do you remember? You can have a fist if you remember none. So 1, 2, I see. So the last one, we're going from benzaldehyde to benzoic acid.
That's the one we just went over.
Ah.
I know 2.
You know 2? That's better than 0 or 1. Anybody know all 5? Maybe? Armand, the human organic chemistry sponge. Just ring them out. All right, so let's do the first one. We've got a primary alcohol and we're trying to go to a carboxylic acid. What do you think we need for this? We're oxidizing it. Yeah, so we need chromic acid.
Oh, I know.
Or we could do the new reaction if we are worried about cancer.
So the last reaction that we covered, the Baeyer-Villiger oxidation, would work for an aldehyde, but not an alcohol, right?
Oh, shit. Wow.
All right, so chromic acid would work really well there. Like we saw way back in second term, it feels like an eternity ago. If it's a primary alcohol, it won't stop at the aldehyde. It'll keep on going to the carboxylic acid. What if we wanted to stop at the aldehyde? Do PCC or Swern, one of those would work. All right, next one. We're going from toluene to benzoic acid. What do we need for this? Same thing. Or if you want to get exotic and use a different one that causes less cancer, you can use potassium permanganate. Usually, every chemist I know would pick the potassium permanganate because it's a lot easier and less harmful to carry out. So it's KMnO4, sodium hydroxide, water, and heat. And then we need to ensure that the final proton's put on. So this is usually followed by some sort of acidic workup to ensure that we're not left with the salt at the end. All right. Next, yeah.
Can you use the KMnO4 for the top one too?
So for the top one, I don't believe you can use potassium permanganate for alcohols, although I might be wrong on that. I think you run into side reactions if you do that. Yeah. All right, next one, we're going from an alkyne, carbon-carbon triple bond, to a carboxylic acid. What do we need here?
O3 and H2O.
O3 and water. If you remember, this is all the way back to like January week 2. So we could cut these triple bonds into carboxylic acids. All right, nitriles. This was kind of hidden in.
Yeah, I don't.
Do you remember when we treated sorry, my brain's not working right now. When we treated aldehydes or ketones with cyanide, the anion, we made cyanohydrins, and I said one of the reactions we could do was to treat that nitrile to convert it to a carboxylic acid. This one's really easy. In fact, it's on your pod. H3O plus. So your task for your problem of the day, and I would challenge you to not crack open your textbook. Trust me on this. Try to do the arrow pushing and just be intuitive, right? So try to follow the common sense arrow pushing that we practiced last term. I'd be willing to bet money you can get there on your own.
Are you sure you want to?
Not a lot of money. All right, last one. What do we need here? Yep, this was the Baeyer-Villiger oxidation, RCO3H. So we have a bunch of tools in our toolbox already where we can accomplish these transformations, but I'll show you a new one that's pretty slick. I'll even put that in here. Slick. All right. All right, so we're going to start out with the Grignard reagent. All right, and our goal with this Grignard reagent is to convert it to a carboxylic acid. And if you're counting carbons here, you can tell we added that new highlighted carbon, and we added 2 oxygens. What reagent do you think we could maybe throw in here to get 1 carbon and 2 oxygens? Don't think too hard about it. No.
Oh, wait. Oh.
Carbon dioxide. You could go over to Fred Meyer right now and buy a brick of carbon dioxide and throw it in your reaction flask with the Grignard reagent. And then step 2, just like we saw before, we need to ensure that this has a proton at the very end because Grignard reagents by their very nature are basic. So we're going to treat this with acid. So we've added in 1 carbon and 2 oxygens. It's pretty good. Let's figure out the mechanism. And let's be careful to draw the Lewis structure for CO2. All right, if you remember with Grignard reagents, we said that this carbon over here is going to have a huge delta negative, and the magnesium is going to be delta positive. In fact, a lot of people even show that carbon with a full negative charge. The reality is it's kind of in between an ionic and a covalent bond because it's so polarized at that point. All right, so that carbon is going to be really, really nucleophilic. It can attack that central carbon and kick up electrons to an oxygen. So one of those oxygens that we have added in would be a negative charge. The countercation will just kind of float around and form an ion pair. And then in the last step, we're going to throw in an acid source to ensure that this ends up with a proton coming right off of it. This is really useful for adding 1 carbon onto things. If we have this carboxylic acid, we can do a lot of things with it, right? We could reduce it to an alcohol. So we could add 1 carbon and then convert it to an alcohol. Once we have the alcohol, we could swap it out for bromine and do substitution chemistry, or maybe we could change it to an aldehyde. There's a ton of tricks you can do with this, but it's really useful for adding 1 solitary carbon to things. Yep. Yeah. Yeah, that's a good point. So why don't we use water in the second step here? Yeah, exactly. In the Grignard reactions, we were trying to protonate alcohols, which are really, really basic. In this case, this intermediate isn't as basic. Why? Because of resonance, right? So it's resonance stabilized, so we have to amp up our acid typically to a stronger acid. Good question. All right, I think we're going to hold off there, but if you want to get started with your problem of the day, you can try doing some of those elementary Arrow-Cushing steps. Remember, just think about it, right? Acid-base chemistry, nucleophiles and electrophiles, what's going to attack where, and try to work from starting to end.